So welcome to my lecture. Thank you everyone for coming. Today we'll talk about bridging technology and tradition with computer-assisted restoration. So let's start with our motivation. So hands up, who has already seen this image before? Okay, not everyone. So this is an example of someone who really don't understand what the restoration process is about. So there was a lady, Cecilia Gimenez, who lived in Boria, Spain, and she was coming to her local church and seeing the mural painting of the Christ getting degraded day by day more and more. So she decided to take a matter in her own hands and make Jesus great again. And this meme, really flown all over the internet, and many people has seen that, okay, not everyone is supposed to do the restoration. And then several years ago, I met one PhD student of restoration, Robert Zemzo, and we decided to get our heads together and started several projects in cooperation of computer science and restoration. So, but first I would like to ask you this question. So this is the process of the restoration of the wooden statue of Madonna from Kurov. And I would like to ask you, what is before and what is after? So we have one of these photos are before the restoration and one of them is after the restoration. So please now raise hands who think that this is the version which is after. So this is already restored. So raise hands. Okay. And who thinks this is restored? Okay, so you are right, yeah? That this is the statue after the restoration and this is the statue before the restoration. And the concept of restoration has historically been a practice that aimed to returning a painting or statue to some idealized original state, with often involved colors, repainting and altering composition and really matching the statue or painting to the taste of the restorers. However, today they are aiming on uncovering all the layers which were painted on the statues and get the somehow original show most they can get from the original state of the painting and conserve it and then really display the art of the original creators of the statues and paintings themselves. So this computer-assisted restoration is a narrow area which can be incorporated to the whole area of cultural computing. So the cultural computing is a field that leverages computer technology and scientific methods to enhance, transform and extend creative processes in culture, art and social sciences. So most of the research I have been doing in the last 20 years can be incorporated in this term cultural computing. So it spanned from helping with some installations of some art installations or some collaboration with psychologists in virtual therapy interventions. But now let's focus on computer-assisted restoration. So this is some non-contact methodology. So when we want to confront it with restoration itself, which is usually very contact, we have some non-contact methodology that employs some digital technologies to reconstruct the appearance of work on art in 2D, in 3D, and we want to help with some conservation reports, preliminary sketches, and to get all these materials together to make or to get more information to the restorers themselves. So and in the literature, we can see 4 different tasks we can help with computer science. And the first one is restoration analysis, then we have restoration documentation, digital restoration, or the presentation of the process itself. And we can say that these 3 tasks are more focused on the restorers themselves, and these 2 are more focused on the public. So we will go through all of these tasks, but first let us divide the whole area of the restoration from the point of computer scientists. So restorers themselves has their own taxonomies. However, from our point of view, we want to divide it based on the data we are working it on 2D and 3D restoration. So let's first focus on 2D restoration. So we will go through all of these tasks, and we will try to illustrate them with some examples from my own research or from the literature. So the first one is the restoration analysis. So in this area, we are currently working on the project which is called Stain Busters, and it's in cooperation with Studio of Artwork on paper and other media. So it's restorers who are focusing on all documents, or maybe mostly all documents. So our goal is to create some kind of app which will detect the stains and recognize its biological origin from the photo. So we start with some photograph or some scan of a historical document. Then we will use some object detection neural network, and then we will create the detection. So we will have some bounding boxes with the class of the stain. Okay, so for those of you who are not familiar with neural networks, I'm not sure if there are some. But we don't have time to go into much details, but we can just say that the neural networks we are using are convolutional neural networks. It has several layers. Some of them are nonlinear, and they are different. All of them are differentiable. So we want to use some gradient optimization to get our results, to find the parameters of the model. So in our task, what is the problem is not the architecture of the model, because there are a lot of architecture we can just take off the shelf and use. However, the problem we are dealing with is data. To train the neural network, we need a lot of data. And in this case, we don't have none. We need our restorers to manually annotate the stains which are on the paper, and this is very time consuming. So we were able to achieve just around 100 images getting annotated with around 1,000 of bounding boxes. And not all classes were represented, because not all classes were present in the archive of Academy of Fine Arts and Design. So what can we do? So we have the problem, we don't have enough data, what can we do? So we decided to team up with microbiologists from Slovak Academy of Sciences, and they can cultivate the stains for us. So we decided to create some kind of semi-synthetic data set where we have a lot of stains made on small paper samples, which get cultivated by the microbiologists in their laboratories. Then we can segment those stains, and then we can render those stains on some historical documents. And we have a lot of scanned historical documents on many datasets online. We have the Europeana, which is great dataset of all documents. So we can definitely utilize these, and in combination with our cultivated stains, we can create a dataset which can be used in this case. So the goal of this project, final goal, we are not there yet, definitely, is to really create a method where you get just one photo and then you will get the result. Okay, there are these type of stains, and be careful, this stain is very dangerous, and just call your nearest restorer and get it restored as quickly as possible, because it will degrade your documents in months, and this can happen. So let's move to the next task, and the second task is restoration documentation and digitization. In this case, we have teamed with restorers from Studio of Photography Restoration, and we were using our high fidelity Cruiser scanner which is similar to one in Slovak National Gallery. So in case you are in need of high quality scans, just contact me or docent Andrej Ferko, and we can give you access to this scanner and you can get really high quality scanned originals. So in this case, we were scanning different old photogrammetric techniques, and we were looking for the best way how to set up the scanners and all the lights so the restorers have the result they wanted. If you want to download the full database, you can use the QR code. Then digital restoration is another task the computer science can help restorers with. So in this case, I was surprised that really restorers themselves were using digital restoration in this area for mostly decades. So they use it in 4 different ways. So first one is as a guide for real-life restoration. So restorers themselves are usually using the Photoshop, and first they just take a photograph of the photo they are restoring, digitally restore it with the Photoshop, and then do the same process with the real original. Also, it can be used as a version to be showcased. So they have an original photo which is very fragile. So they just conserve it, store it somewhere, and print the digitally restored copy and display it in the vitrine or in the showcase somewhere in the gallery. Then it can also be used as a version to be printed or presented digitally. So they as well conserve the original and just use this digitally restored version to be printed, for example, in some book. And the fourth one is you can also use it as a new original. I have found examples of these in the literature. So, for example, they have the statue and the part of this object where the photographs which were sticked on the statue. And the bottom part get wet and they get degraded, so they decided to scan these photos, then digitally restore them and print them again and stick them on the statue itself. So, and what can be used, they are usually using some kind of semi-automatic digital restoration with usually Photoshop, as I asked them, but there are some ways to do it automatically with, once again, some neural networks. Okay, let's get to the fourth task of computer-assisted restoration for 2D, and in this case, it's a presentation. So in our project, where we were teamed with the restorers of historical photographs, we decided to create something which we called restorer's point of view. So we wanted to show audience what the restorer themselves are focusing on when looking for the first time on the original they want to restore. So we decided to create this kind of saliency heat maps. So in the areas where it is really red, it means that the restorer themselves really focused on that part of the image. And we decided to use eye tracking using Tobii glasses. So in this case, Tobii glasses essentially measure 3D gaze vectors, or gaze vectors in 3D space. And these glasses has infrared LEDs, which are facing inward, as well as 2 inward-facing cameras, and it has also forward-facing cameras. So what we want to achieve, we want to know where the user is looking at in the video, which is captured while he's wearing the glasses. So each frame, the system creates some infrared pattern, which is projected on your cornea, and then some geometric eye model is fit, and we determine the pupil center, optical axis, and then based on it, we can estimate where the user is looking at in the video of the scene. So now we know where the user is looking at the video, but what we need to do is we need to somehow accumulate all the points through whole video where the user was looking at the concrete example of object, in this case, this historical photograph. So we need to somehow estimate the transformation from the video with marked gaze point of the user to some template version of the image. And we can do this using homography. So we can do it in we can compute it in different ways. In one case, we can have 4 stable points. And in this case, we can compute it directly. We have homogeneous coordinates here, and we have just 8 degrees of freedom. And in this case, we just need 4 point correspondences, and we can directly compute it. However, sometimes we don't have 4 stable points. For example, the restorer will come really close to the photo and we can't see the corners anymore, and we don't know how to, what is the correct matching with these corners with the original photo. So how can we solve it? Okay, so we don't have 4 stable correspondences, but we can have a lot of correspondences with some possible outliers. So what can we do? We can use RANSAC. I don't know if all of you are familiar with this method, but we will go just briefly through it. It's some iterative method to estimate some parameters of some mathematical model from a set of observed data points that we think contain some outliers. Okay, so let's illustrate it in some easier example. So in this case, we are looking for a line. In 2D, we just need 2 points, 2 parameters. So we are looking for a model with 2 parameters. So this is just an easy algorithm. We will randomly sample these points. Then we will estimate the parameters of the model. We will evaluate the error function. Then we will identify points consistent with our model, and we will iterate through this. So let's have some nice codes, like some of us are from computer science, so let's see the algorithm itself and go through it. So first we need to randomly pick some samples. So in this case, our model just needs 2 samples, so we have 2 points. Then we will fit our model. In this case, it's just a line. Then we have at first our set of inliers is empty set, and we will go through all the point set and estimate the error function. So then, based on some threshold we picked in advance, we know which of these points are inliers. And then we will iterate. So K2, K3, and so on until Kn. And then we will pick the best one. So we will pick the best model. We know which are the inliers. And you can ask, okay, and how do we know how many iterations should we have? So we can easily compute it with the fact that to know how many iterations we will need, we need just enough iterations so that with some probability p, at least 1 sample of size m, so in this case 2, contains no outliers, given some outlier ratio r. So in our case, it works like this, that we will use RANSAC, so we will have some local features extracted at each frame of the video. We have local features extracted from this image. We have the pairs between them, and from these pairs we will, in RANSAC manner, compute the homography. And in our case, we have a sample of size 4. And if we estimate that plus minus 25% of the matched pairs are outliers, we will need at least 13 iterations on this. If we are okay with probability of 0.99. Okay, and then later we can have image like this and show the audience what the restorer themselves are focusing at if looking on photographs to be restored. In this case, you can see that they are focusing on some degraded parts of the image, but as well, restorers are human. Yeah, that's true. And they are looking at the faces, as all of us do. So now let's move from 2D to 3D, and we will go through these 4 tasks on computer-assisted restoration, and in this case we will do it in 3D. So first thing I want to mention is that most of these projects we were doing were originally in collaboration with Slovak National Gallery. But however, it's a pity, but the Slovak National Gallery was due to incompetence of politically assigned leaders. A large number of Slovak National Gallery employees submitted collective resignation early this spring, and many of them have since continued their professional work elsewhere. And our main collaborator, former head of digitization at Slovak National Gallery, Branislav Horniak, moved to Bratislava City Museum, and now we are happy to continue our collaborations there. But yeah, it's a pity. So when we want to do anything with 3D and help the restorers with 3D, first thing we need to do is do some 3D reconstructions. So to do this, the 3D reconstructions of cultural heritage and digitization of 3D cultural heritage is a hip topic since 2000, when this great group of computer graphics people from US came to Florence and digitized Michelangelo's David in this project called Digital Michelangelo. They used laser scanners. They use laser scanning, which acquires geometry by directing a focused laser beam over the object surface and recording either the angle of reflection or, in some cases, a time delay of the return signal in the time-of-flight manner. And this produces dense, metrically accurate point clouds, often with sub-millimeter precisions. However, in the area of cultural heritage, more techniques are used. We can also use structured light scanning, which reconstructs surface geometry by projecting some known line patterns from the projector, such as stripes or grids. It can also be the sequence of patterns. It can be in visible spectrum or infrared. And when we capture their deformation with a camera, we can estimate the depth of individual points. So, yeah, this approach can be used. And in my second lecture, I will show you how we were using this structured light scanning for our project for digitization of cultural heritage. But most common these days is to use photogrammetry for 3D reconstruction of objects, and it is considered a golden standard for digitization of cultural heritage in most national galleries and museums all over the world. So this is the pipeline. We are going to go through it very briefly. Don't be scared. So first, we need to do some preparation and setup. So we need to have some diffuse lighting. We want to get rid of the shadows and some specular reflections. Sometimes we want to use some polarization of both cameras and lights. We want to use sometimes a rotary table. Maybe we will calibrate the camera at first. Then we will do the image acquisition. So ideally, we will have an overlap of 60 to 80% between individual images, and we will have many of them from different positions, elevations. We will rotate around the object. In Slovak National Gallery or similar digitization settings for statue of this size, 10,000 of images are usually used. So it's crazy big amount. Then what we are going to do, similarly to an example with the heat map, we have to find local features, so locally interesting points, and we need to describe them with some descriptors. There are a lot of methods in traditional computer vision, and also you can use some learnable methods. In traditional computer vision, we have methods like SIFT, SURF, FAST. There are a lot of them. In neural networks, we have superpoint or Roma features. Also, like a lot of methods are used. We can pick one. Then we want to proceed to a feature matching. We can once again do some ransack here, which was already introduced. And then we will move to the structure from motion. So what we want to do, we are going to do incremental structure from motion. So once the pairs of the points are estimated, so we know we will pick first 2 cameras and we will estimate their relative pose, so their relative translation and rotation. And in this case, we can also do it with RANSAC. We will have some set of polynomial equations here. These relative pose can be estimated by essential or fundamental matrix, but yet we don't have the time to go into details. But what you want to know is we have, right now in this step, we have just set of 2D correspondences. So we have 2 cameras, we will estimate the relative pose of these 2. And then it's incremental structure from motion, so we incrementally add more cameras. So we have 2, we have estimated this relative pose, we will add another camera, and now what we have is we have already triangulated points from the first step. So now we don't have 2D anymore, but we have 3D points with 2D projections in the next camera we edit. So in this case, we can solve another system of polynomial equations. In this case, is P3P problem, and we can do it as well with RANSAC this time. And when we estimate, this is not relative pose anymore because we have fixed points in 3D, so we are estimating absolute pose of these cameras, and we can retriangulate the points, so we can estimate the better position of the points where one triangulated, and we can even add more and more points from more and more cameras. Okay, problem. So this is iterative process. So when we have small error at first, these errors, we can add thousands of images. I say that in some cases, 10,000 of images. So these small errors really accumulate. And what can we do to not get into the catastrophe is that we need to stabilize this project, this process, and it can be done with bundle adjustment. So what we are going to do here, so we want to minimize reprojection error. So we have this 3D point, which is projected to this point in some camera. This is also, not all points are visible in all cameras, so we can make them visible or invisible. And we want to jointly refine for all of the 3D position of all of the points, and at the same time for all of the poses of the cameras, so rotation and translation for all of the cameras. So this is the bundle adjustment. It is done to really stabilize the whole project, whole process of incrementally adding the cameras. And yeah, you just need to know it's some minimization of this reprojection error. Okay, so we have done these 5 steps of photogrammetry very quickly. We go to these 4 more steps even quicker, so don't be scared. So we have sparse point cloud. So we get some of the points, but we need to get to the dense point cloud because we want to have our statues very nicely done, not with very few triangles, but with lots of them. So we are going to estimate the depth also for all the other pixels of all the cameras with multi-view stereo techniques. Then we are going from the dense point cloud to mesh, so we will have representation in triangles. Then we will do some texture mapping. So we have our mesh and we have like all the photographs, and we will project the textures onto the mesh. And then we can have some post-processing and analysis, so we can remove some artifacts and export it in different formats to be used for visualization or restores themselves or digital archiving, whatever you can imagine. Okay. So I have introduced this photogrammetry pipeline. However, if we want to be really state-of-the-art, so this is done by all the galleries, all the cultural institutions, but however, in the literature, nowadays, these novel view synthesis methods are used for visualization of some 3D objects from the photos. So we have these very HIP papers of nerve and Gaussian splats. So maybe you have heard about them. So in the case of nerves, we have a neural network which learns a continuous volumetric function. And as an input, we have 5D input, and the 5D is x, y, z of some point. And then we also have the viewing angle. So we know from which point we are viewing the point. Yeah. And what is the output is the color and the density of the point. So if we want to then create the novel view, so we will it's similar it's somehow similar to the ray tracing manner when we will have a lot of rays and compute like what can be seen in on the different rays. So then we will reconstruct the view from the novel point. And then we can have another representation, and it's called Gaussian splats. And in this case, the scene itself is represented as a set of 3D anisotropic Gaussians, Gaussian primitives, who has some position, scale, opacities, and colors. And it's optimized from input images. So both of these, you need a bunch of images very similar to the photogrammetry. So in case you are using photogrammetry pipeline, you will just, do these first two steps. In some cases, you, in Gaussian splats, you also get to the fifth point. So you will have a structure for motion and then continue with the Gaussian splat representation. So here SFM points. So after the S structure for motion step, you will just use the Gaussian splats to visualize it, or you will just need images and use nerve to visualize it in this way. So these are novel techniques which are currently in the literature. This paper from 2023 already has like 6,000 citations, so it's very hot topic in this area. But however, I'm not aware that anyone in like museum or gallery setup is using this right now. Okay, so now we have our 3D reconstruction, so we can do some nice computer-assisted restoration with these 3D models. So the first one is restoration analysis. So in 2D, we were using these stain busters, and in 3D, we can help with some textures which are multispectral. So doing infrared imaging and UV fluorescence imaging is not novel at all in restoration. They have been used for ages. However, if we have a 3D model, we can do these textures from different points of view, and we can register them with the 3D model. So we can add the context for the restorer, not only to see it as individual photos, but they can see it mapped on the 3D model and can get more context from it. So, for example, infrared imaging can be used to uncover some hidden layers. In this case, this San Sebastian statue has painted veins, but they were later covered by another layers of paint by some restorers in 19th century because they seem vulgar. And right now they can see it without doing some destruction on the statue, and they know how big or how many layers they need to uncover to get to this. Okay, we also can help with not only seeing from outside, but we can see inside of the statue, and using the CT scanning, we can see some hidden structures like nails or some holes or joints, cracks, hollow areas, which are invisible from outside. So in this case, Restore themselves are using medical CT scanners, so they usually just travel with their statue to some hospital and they will get the CT scan. However, the visualization tools for these data are usually really focused on the soft tissues of the human body. So if they want to see the wooden structures and the nails inside, the software which is used is not very suitable for this one. So we are currently collaborating them to create some kind of visualization tool for them to see what they want to see in the CT scans of the statues. Okay, so let's go to the second task of the 3D computer-assisted restoration. Restoration documentation. So I have already talked a lot about 3D scanning. I just want to mention that right now we have this very nice KEGA project, which is focused on empowering restorers themselves to learn how to use photogrammetry tools to create their own 3D reconstruction of their own restoration processes. So, it's fun. We have a lot of students from the restoration there, and after the small workshop, a one-day workshop, they are able to use software like Polycam to create their own 3D reconstruction of their statues. Okay, so let's move to digital restoration. In this area, I haven't done any research yet. Maybe later, hopefully, but there are a lot of examples from the literature. There is also we can see the overlap with archaeology. And for example, this Rome Reborn is some archaeological reconstruction of the Forum Romanum in Rome. Maybe you have seen it before, but also like maybe on ancient or on Neolithic pottery, you can also see some digital restoration of these pieces of it. So it's definitely many different research was done in this area, but these are just some examples to illustrate it. Okay, so we are going to the last task of the computer-assisted restoration, which is called the presentation. And in this case, we have introduced something which was called virtual showcase. So it's basically view-dependent stereo for those who are familiar with this concept. So in this case, we use the camera and the passive 3D display. This recording is not on that passive 3D display because then you will see it very blurry, but it's on my computer, just this one, so it's not that nice. But the concept of view-dependent stereo, as you can see here, is that we are doing the real-time rendering, where we are tracking the head of the user and re-rendering the image or the 3D virtual scene as the statue itself will be inside of your display or behind the display, let's say. So we are tracking the user and we are re-rendering it all the time. So we have different setups of these, and this virtual vitrine was used as an exhibition in Stará Pošta Gallery 2 weeks ago. It ended. So yes, so in this way, when we capture the process of the restoration, so we will do the photogrammetry in different phases of the restoration, we can then use these kind of devices, or we can use VR, and we can create an exhibition where we present this process to general public. Okay, and just sorry, I don't know where's my cursor right now. And just to sum up, as a conclusion, I think it's important to educate people about the restoration processes. And I think that computer vision and extended reality can help us with that. And I also think that interdisciplinary research is very hard, but it's rewarding. And when I was a high school student, I thought that maybe I will go to study to Academy of Fine Arts, but I was not very...
Dobrý deň. Pardon.
Okay, so you have Santa Claus here. Yeah. But I was not very skilled on drawing, so then I decided to go study computer science, but somehow I got back to art. So when you would like to go study art, go study computer science instead. and you can come back to it later. Okay, so thank you for your attention, and I'm happy to